Okay. So make sure when you're reading the statement, slow down a little and make sure that you understand the given situation correctly. Rajesh applies once every year for a ticket to a music festival. The probability that he's successful in any particular year is 0.3 independently of other years. Now he is applying once every year. So something is happening again and again, right? There's repetition. Something is happening again and again. It's repeating. The probability that he's successful in any particular year is 0.3. And it's independent of other years. That means it remains the same every year, 0.3 every single year. We need to find the probability that Rajesh is successful for the first time on his 7th attempt. Now, that's a very standard keyword for a particular type of distribution. What distribution is that? That's geometric distribution. In geometric distribution, we talk about probability of getting our first success on a particular outcome. So this is a geometric distribution because we're talking about first success. Okay. So we say this is a geometric distribution. What is it that we're looking for? Probability that the first success comes on the 7th attempt. What's the formula that we have for geometric distribution? It looks like this: probability that x equals r, that is q raised to power r minus 1 times p. That's the formula that we have for geometric distribution. If the probability of success is 0.3, what about the probability of failure in this case? That will be 1 minus 0.3, which is 0.7. Just input values in the formula. It will be 0.7 raised to power 7 minus 1, which is 6, times 0.3. So you have 6 unsuccessful attempts, right? And then the 7th time he is successful. And that gives you the result. Okay, I would really appreciate if you can help me with the calculation so we can do it relatively quickly. So what do we get with this from this? 0.7 raised to power 6 times 0.3. What's the answer? 0.03532 significant figures. Thank you. 0.0353. Now that was a standard geometric distribution. Okay. Let's look at the second part now. In the second part, it says, find the probability that Rajesh is successful for the first time before his 6th attempt. Now we're still talking about first success. He is successful for the first time. So we're talking about first success, okay? But that first success, what's the probability that it comes before his 6th attempt? So what that means is we are looking for probability of x being less than 6, right? That's the probability that we're looking for. Probability that the first success comes before the 6th attempt. Now, it's a geometric distribution. For a geometric distribution, we have a formula for inequalities as well. And that's this. This is what you need to remember. You should memorize this. There's a logic behind it. But can't go into that right now. Probability of x greater than r, that equals q raised to power r. Okay. You need to remember this formula. This formula is not given in the formula sheet. For a geometric distribution, probability that x is greater than r is equal to q raised to power r. We will remember this formula. Now, is it that form that we have given there? No, it's not that form. This is less than 6. The formula is for greater than something. We need to convert this to greater than form. Okay, now let's write it down. Less than 6. What does it mean? Less than 6 means the first success could come on the first attempt. It could come on the second attempt, the third attempt, the fourth attempt, fifth attempt, and that's it. It should not come after 6. So 6, 7, 8, 9, and so on. These have to be excluded. What other way can we write this probability so that we have the greater than form? What we can say is total probability for all of these numbers, that is 1. We can subtract from 1 the probability of all of these numbers. 6, 7, 8, 9, 10, on all the way up to infinity. We can subtract from 1 probabilities of all of these numbers. How do we do that? How do we describe this in greater than form? numbers from 6 onward, we can say these are greater than 5. These numbers are greater than 5. So we can say it's 1 minus probability that x is greater than 5. What does that give us? 1 minus q raised to power r, and that's just q raised to power 5. And that should give you the result 1 minus 0.7 raised to power 5. You can get your answer from that. What's the result that we get? What's the answer that we get from this? 1 minus 0.7 raised to power 5. .832. Okay, so this is what we're getting, 0.832. Thank you. That's the final answer. Yes, Ima.
Assalamualaikum, sir. Wouldn't it be greater than equal to?
Greater than equal to? So
yeah,
less than 6 means we want the numbers 1, 2, 3, 4, 5. Right? These are the numbers that we want. What are the numbers that we don't want? We don't want 6, 7, 8, 9, 10, all the way up to infinity. We want to describe these numbers from 6 onward. How do we describe them? We could either say they are greater than or equal to 6, but the formula that we have is for greater than. In greater than form, we can say numbers from 6 onward, they are greater than 5, right? So it should be x greater than 5. That's what we subtract from 1. Does that make sense?
Yes, sir.
Yeah, okay. All right, that was part B. Now it says, find the probability that Rajesh is successful for the second time on his 10th attempt. Now, is that geometric distribution? Second time on his 10th attempt. That's not geometric. Geometric distribution talks about the first success only. Now we're talking about second success. Now, that's not any standard distribution, but that's a type of question that you will see a lot of times in recent papers. It's getting repeated again and again. Let's think of it this way. You have first attempt, second attempt, third attempt, fourth attempt, fifth attempt, 6, 7, 8, 9, and then 10. 10th attempt is supposed to be a success. 10th attempt is supposed to be a success. Okay? But it has to be the second success. It should not be the first success. It should be the second success. That means we should have exactly one more success in the first 9 attempts, right? So out of these first 9, there should be one other that is also a success. That is when the 10th attempt would end up becoming a success. Okay? So how do you find the probability of there being one success in the first 9 attempts? Now, this is something that we can classify as a binomial distribution. That in the first 9 attempts, we have one success. So we consider 1 to 9 as a binomial distribution. We say it's a binomial distribution with how many repetitions? 9 repetitions, 9 attempts. Probability of success, 0.3, just like before. Probability of failure, 0.7. We want exactly one success out of these 9. What's the formula for binomial? NCR p raised to power r q raised to power n minus r. Okay. Let's input values on that. 9c1 into 0.3 raised to power 1 into 0.7 raised to power 9 minus 1, which is 8. And that will give you some result. What's this? What do you get from this? 0.15. Okay. Don't round it off yet. This is not our final answer. 0.15565. Okay. This is what we're getting. Okay, that's the probability that you have one success in these 9 attempts. And then the second success comes on the 10th attempt. What's the probability for that? Probability of having a success, 0.3. So what we would do now is we would multiply this number 0.15565 with 0.3, and that will give us the result. This is the probability of having one success out of first 9. One success out of first 9. That's this number. And this is the 10th being a success. Okay, this is just for your notes. You don't have to write it down in the exam, but you multiply this by 0.3 at the end, right? That's the probability of having success in the 10th attempt. So you multiply this by 0.3 and see what that gives you. That's 0.04669. That becomes 467. That's your final answer. Game. Players attempt to score a goal by kicking a ball into a net. The probability that this person, Leno, scores a goal is 0.4 in any attempt. So the probability remains the same. That's not changing independently of all the other attempts, right? The random variable x denotes the number of attempts that it takes Leno to score a goal. Number of attempts required to get a success. First success. What does that remind you about? Score a goal, that means that's the first time that she is scoring a goal, right? Number of attempts it takes her to score a goal. That's geometric. That's a geometric distribution. So it's a geometric distribution with probability of success of 0.4. And what about probability of failure then? That's 0.6. We want to find the probability that x is equal to 5. X represents number of attempts. Okay. What's the probability that you get your first success on the 5th attempt? The formula for geometric distribution that looks like this. Probability of x equals r, that's given by q raised to the power r minus 1 times p. Right? So we say this is equal to 0.6 raised to power 5 minus 1, that's 4, times p, that is 0.4, and that's what give you the result. You can see what that is. What's this number? .0518. Okay, that's the final answer that we get, 0.0518. Now it says find the probability that x is between 3 and 7. X is between 3 and 7. So it can be 3 or 4 or 5 or 6 or 7. These are the 5 possibilities that we've got. Now, that's a limited number of values. If we want, we can calculate them separately, and that should work. So one way of doing this could be that we say this is the same thing as saying probability of x equals 3 plus probability of x equals 4 plus probability of x equals 5 plus probability of x equals 6 plus probability of x equals 7. That's 5 probabilities. If you want to calculate all of them, that works. You can do that. You can say the first one is 0.6 raised to power 2 into 0.4. And the second one, that's 0.6 raised to power 3 into 0.4. And then 0.6 raised to power 4 into 0.4 plus 0.6 raised to power 5 into 0.4 plus 0.6 raised to power 6 into 0.4. Now, when you put this on your calculator, you can take 0.4 common outside. So you don't have to write that again and again. And then you can write down the answer. Okay, that's one possible way of doing this. Since it's only 5 values, it is possible to do it like this. Okay, it is possible to do it like this because it's only 5 values. So you can do it like this. All right, I'll tell you the other method as well. So in your calculator, you could put it like this, take 0.4 common, then inside you say 0.6 squared plus 0.6 cubed plus 0.6 raised to power 4 plus 0.6 raised to power 5 plus 0.6 raised to power 6. And that should give you the answer. This is giving me 0.332 to 3 significant figures, and that could be your final answer. This is one way of doing this. It works. It's only 5 values, you can do that. But what if they had said between 3 and 17? Then you would be stuck, right? That's too many calculations. 3 to 7 already, it was fairly long. What if it was 3 to 17? So we need to know, we should know another method for this as well. And that's using inequality formula. So remember, for a geometric distribution, there's another formula that we have as well that you should memorize. And that is probability that x is greater than r, that is equal to q raised to power r. For binomial, we don't have any such formula. For geometric, however, we've got this direct formula as well that we can use. Probability of x greater than r, that equals q raised to power r. Now, how would we use that? We want to convert this probability in greater than form somehow. Okay. Now, how would we approach this? This is one way to think about this. Let's write down the numbers that we need. We need 3, we need 4, and then 5 and 6 and 7. These are the 5 numbers that we need. Okay. What we do not need is numbers on the left side, and the numbers on the right side. Those are the ones that we do not need. So we don't need 1 or 2. We do not need 8, 9, and all the way up to infinity. We don't need all of those numbers. The only thing that we want is these 5 numbers. Okay, that's what you want. Now, in greater than form, how can we describe these 5 numbers in greater than form? We could say all of these numbers are greater than 2. So we could say, let's consider all of these numbers first of all. From 3 onward. How would you describe these numbers? These numbers are greater than 2. So this black line that I've drawn, this represents numbers that are greater than 2. I want to write the numbers in greater than form, right? So from 3 onward, we could say they are greater than 2. Now, that also includes these numbers 8, 9, 10, 11, 12, and so on. I want to get rid of them because I only want the numbers in the middle here. I only want 3, 4, 5, 6, 7. So how do I get rid of 8, 9, 10, and so on? I can subtract from this these numbers from 8 onward. How would I describe those numbers in greater than form? These are numbers that are greater than 7. So I can write that probability as probability of x greater than 2. That will incorporate all of these numbers. Subtract from that probability of x greater than 7. That will be all of these numbers. So I get rid of those numbers, and that will leave me with only these yellow shaded numbers. Now, this is something that I know how to calculate. Probability of x greater than 2. The formula is just q raised to power r. So it becomes, what was q? 0.6. So it becomes 0.6 raised to power 2 minus 0.6 raised to power 7. Evaluate this, and that should give you the same result. That's 0.332. So you don't have to do all of these calculations like this. It's possible in this case because it's only 5 values, but if it was more than that, this is the method that you should be able to use in that case. Is that okay? Find the probability that Dana scores his second goal on or before his 5th attempt. Again, we have done this question multiple times before, similar questions. Second goal should be scored on or before his 5th attempt. So let's write down the attempts. Let's say you've got the 1st attempt, the 2nd attempt, the 3rd attempt, the 4th attempt, and the 5th attempt. So I've represented the number of attempts like this. Okay. The second goal should be on or before his 5th attempt. Okay, now this is actually trickier than before because it says on or before his 5th attempt. That will require us to use a number of cases actually. The second goal is scored on or before his 5th attempt. So one possibility is that the second goal is scored here. Another possibility is the second goal is scored here or here or here. Wouldn't that be too much calculation? Because we have to consider multiple binomials here. Okay, so let's do it the same way that we used to do before. And that was one possibility is that the first goal is scored here and the second is scored here. Or if we were to write down all the possible cases, that could also work. Just think about it. This is the first possible case, then second. Okay, so I'm going to do it the first way first, the way that we used to do it earlier. We'll have to make cases here because it's not saying that the second goal is scored on his fifth attempt. It could be before the fifth attempt as well. So case one would be that the second goal is scored on the second attempt. Okay. Now, if the second is scored on the second attempt, then the first has to be scored on the first attempt. What's the probability for this case? This would just be probability of scoring the first time. What was that? 0.4 times 0.4. That will be the first case, that the second goal is scored on the second attempt. Okay. Case two would be that the second goal is scored on the third attempt. All right. But then the first goal could come in any one of these two attempts. So there has to be one more goal scored in the first two attempts. So this we can consider a binomial like we used to do before. It's a binomial with n equal to 2. And we want one success here. Right? We want one success. Probability of x equals 1, one success. What will be the probability for that? Out of the first two attempts, we want one success. What's the binomial formula? NCR, p raised to power r, q raised to power n minus r. Out of the first two attempts, we want one success. So that will be 2c1 into p, which is 0.4 raised to power 1 into 0.6 raised to power 1 times this third attempt, that is a success. We multiply this by 0.4. Now what I'll do is I'll try to color code this. So the second attempt, I'm going to represent that in green. Okay. So the first case was the first attempt is a success, the second is a success. The second case is the second success comes on the third attempt. So we've got the 0.4 for that. The first success could be any one of these two. So for that, we're using binomial that out of the first two, we have one success. Okay. Out of the first two, we've got one success. Case three. Case three would be that the second success comes on the fourth attempt. Now that means in the first three attempts, we want one success. So this is a binomial with n equal to 3, and we want one success here. What will be the probability of that? 3c1 into 0.4 raised to power of 1 into 0.6 raised to power 2, that out of the first three attempts, we want one success. And then there's a success on the fourth attempt as well. The probability of that is 0.4. We multiply by that. And then the last case would be that the first success comes on the second success comes on the fifth attempt. That means amongst the first 4 attempts, we want one more success. So this is a binomial with n equal to 4, and we want probability of one success in those 4 attempts. That will be 4c1 into 0.4 raised to power 1 into 0.6 raised to power 3 And then we have another success here, that is 0.4. So you calculate the probabilities for these cases, you add them up together, and that's going to give you the final result. Any questions on this? This was quite complicated. But if you remember the other similar questions that we've done before, it's that same question, but with more cases that you end up having to consider. But the idea is the same. Why do we consider the fifth success? Because it says on or before. So the second success could come on the fifth attempt as well. We are considering the fifth attempt because the second success could come on the fifth attempt as well. That's what the question says, right? It could be on or before. So we have to include the fifth as well. Why are we using binomial? Because the question says the second success has to come on the fifth attempt, on or before the fifth attempt. So let's just focus on one of these cases. Let's consider the last case. The last case is saying that the second success comes on the fifth attempt. So now we know this is the second success. On the fifth attempt, we have the second success. Now, if that is the second success, there has to be one more success in the first 4 attempts. So out of the first 4 attempts, we want one success. So we're talking about probability of a certain number of successes. We want one success out of the first 4. That's binomial. Probability of having a certain number of successes, that's binomial distribution, right? So for the first 4, we say we are repeating something 4 times. What's the probability of getting one success out of those 4? So for the first 4 attempts, we use binomial in this last case. And then we multiply the probability of success in the 5th attempt, that's 0.4. And that gives us the probability for the last attempt. And similarly, for the other cases as well. Does that make sense? Is that all right? Okay. Now, you could think of it yourself as well without using binomial. You could think of it logically as well. So basically, binomial distribution. So Nabiha, what you're saying is, if you remember when we started binomial distribution, we learned where this formula comes from, right? How we derive this formula. So it comes from permutations and combinations, right? So you can do that whole working yourself as well without explicitly thinking of binomial. So let me do it that other way as well now. Without thinking of binomial, you could also do it that way. So you'll be doing exactly the same thing, but without the formula. Okay, without the formula. Let's try it that way. So again, we have to consider cases. The cases are case 1. The second success comes on the second attempt. Case 2 is the second success comes on the 3rd attempt. Case 3 is the second success comes on the 4th attempt. And case 4 is that the second attempt comes on the 5th attempt. So these cases are fixed. This is fixed, this is fixed, this is fixed, this is fixed in each of these cases. Now, for the first one, the first success has to be in this position, right? Okay, so that means that's just going to be 0.4 into 0.4 for the first case. For the second case now, we've got 0.4 for this. But the first success, the probability of that is 0.4. But that could either come here or it could come here. right? It could come in any one of these two positions, right? The first success could either come here or it could come here. We've got two possibilities for this. So we have to consider both of these possibilities. Now, how do we do that? Let me write it like this. We have two successes in total, right? So for all of them, we are actually going to get, for the rest of them now, we're going to get something like this. If we are making 3 attempts, that means there are 2 successes and 1 failure. So we can do it like this. This is 0.4 squared because we're getting 2 successes and 1 failure, that's 0.6. But then in how many ways can you arrange these? So we can either have this first success and this failure, or we can have this success and this failure. So there are 2 possible ways of arranging that. Okay, 2 possible ways of arranging that. So we multiply this by 2 for that reason. We multiply this by 2 or 2C1 because there are 2 possible ways of getting that success. You could either get that here or here. In the third case now, there are 4 attempts. 2 of them have to be successes and 2 of them have to be failures. So we have 0.6 squared and 0.4 squared. In how many ways could that first success come? It could come in the first attempt or the second attempt or the third attempt. There are 3 ways of placing that first success here. So what you do is you multiply this by 3. And then in the last case, you've got 5 attempts in total. That will be 3 failures and 2 successes. In how many ways can you arrange, in how many ways can you place that first success? 1, 2, 3, 4. It could come in 4 different positions. So we multiply this by 4. And now if you add all of these numbers, that should also give the same result. All right. This could be another way of thinking about this. If you want to do it this way, that's also possible. Now you just add all of these numbers up and that should give you the result as well. Okay, what's the final result that we get when we add all these numbers up? What's the final answer that we get? Just have one part left. Hopefully my iPad can survive. What's the final answer? .663. Okay, thank you. That's the final result that we get. 0.663. That's the final answer. No problems. Okay, so this was question 3 from this paper. Let's move on. The next one that you have from this paper is question number 5. Okay, so, and that's the last one. Question number 5, let's try that. Question 5 from this paper. No permutations and combination questions today. That's surprising. So you're fine with those questions now? Permutations, combinations. A factory produces chocolates. 30% of the chocolates are wrapped in gold foil. 25% are wrapped in red foil, and the remainder are unwrapped. Okay. 30% gold foil, 20% red foil, and then the remaining are unwrapped. What's the remaining? That will be 45%. Right, that's unwrapped. Indigo chooses 8 chocolates at random from the production line. Okay, 8 chocolates are chosen at random. Find the probability that she obtains no more than 2 chocolates that are wrapped in red foil. No more than 2 chocolates that are wrapped in red foil. Now, how do you think about this? Can we treat this as binomial distribution? Can we treat this as binomial distribution? It's a factory. It's a factory that's producing a large number of chocolates, right? Factory producing large number of chocolates. If we take one chocolate out of it, it doesn't really affect the total number of chocolates as such, right? So probabilities, we can say they will remain constant, right? So when you've taken one chocolate out, for the next chocolate, the probability of it being in the gold foil or the red foil or being unwrapped, the probability will remain constant, right? It's the change is going to be negligible, that we can think of it as remaining constant. So probability is constant. We can think of it as two possible outcomes, because what we're looking for is probability that the chocolates are wrapped in red foil. So we can call this our success criteria. Then if it's not wrapped in red foil, we will say that's the criteria for failure, right? So we have two possible outcomes, and we have something being repeated. We are taking a number of chocolates. We're taking 8 chocolates in total. So that's your value for n. This is the criteria for success. We can treat this as binomial. So for this binomial distribution, the value for n, that is 8, probability of success is that it's wrapped in red foil. That probability is 25%, that's 0.25. Then the probability of failure would be that it's not wrapped in red foil, that's 0.75. Probability that she obtains no more than 2. How do you write that as an inequality? No more than 2. Is 2 possible? Yes, 2 is possible. More than 2 is not possible. So it could be either 0 or 1 or 2, right? That will be no more than 2. So you'll say it's x less than or equal to 2. So we have 3 cases. Either it could be 0 success, or you could have 1 success, or you could have 2 successes, right? So you could either have 1 chocolate wrapped in red foil, 2 chocolates wrapped in red foil, or 0 chocolate wrapped in red foil. Just add up all of these probabilities. What's the formula? NCR p raised to power r q raised to power n minus r. You can see what that turns out to be. N is 8, so that's 8C0 into p, which is 0.25 raised to power 0, into 0.75 raised to power 8 minus 0, which is 8, plus 8C1 into 0.25 raised to power 1 into 0.75 raised to power 8 minus 1, which is 7. And then finally, plus 8C2 into 0.25 raised to power 2 into 0.75 raised to power 8 minus 2, which is going to be 6. Put this in your calculator and see what that gives you. That will be the final result from this. What do we get for this? Okay, thank you. 0.679. That's the final result that we get. Okay, so rounded off to 3 significant figures. This is what you get. Now it says Jake chooses. So now that's a different person. Jake chooses chocolates one at a time at random from the production line. Find the probability that the first time he obtains a chocolate that is wrapped in red foil is before the 7th choice. First time you're choosing something. What does that mean? First success. What does that remind you of? Geometric distribution, right? So now it's geometric distribution. Probability of getting your first success on a particular attempt, that's geometric. What's the criteria for success? They're talking about wrapped in red foil again. Probability for that was 0.25. So probability of success is 0.25. Probability of failure, that's 0.75. Probability that the first success is before the 7th attempt. Before the 7th attempt. How do you write that down? Before 7, that's x less than 7, right? X less than 7, before the 7th attempt. Now it's a geometric distribution. 0 is not possible. You can have 1, 2, 3, 4, 5, 6. So one possibility is you add up all of those numbers. Probability of x equals 1, 2, 3, 4, 5, 6. However, for geometric distribution, we also have a formula for inequalities, remember? What's that formula? The formula is probability of x being greater than r, that is equal to q raised to power r, right? Now, can we convert it to a form like that somehow? The formula is for greater than, and here we have less than, so that means we'll have to do 1 minus something, right? 1 minus something. Now, 1 minus what? That's what we have to think about. Let's write down some numbers that will make it easier for you to think about this. 1, 2, 3, 4, 5, 6. These are the numbers that we want. What are the numbers that we don't want? 7, 8, 9, 10, and so on. These are the numbers that we don't want. How do we describe these numbers that you do not want? In greater than form. How do you describe these numbers? These numbers are greater than 6, right? So you say it's 1 minus probability of x greater than 6. You subtract from 1 the probability of x being greater than 6. What does that evaluate to now? 1 minus q raised to power r, that's q raised to power 6. So that's 1 minus 0.75 raised to power 6. Put this on your calculator, you'll see what you get. 1 minus 0.75 raised to power 6, and that's 0.8220 to 3 significant figures. That means 0.822, and that's your final result. Is that all right? Simple geometric distribution, use of the inequality formula. Let's look at the next one now. Now there's a third person. She chooses chocolates one at a time at random from the production line. Find the probability that the second chocolate chosen is the first one wrapped in gold foil, given that the fifth chocolate chosen is the first unwrapped chocolate. Okay, so I think the trickiest part of this question is trying to understand what they're saying here. Let's break it down. Probability that the second chocolate is the first one wrapped in gold foil. Okay, so that's the probability that we want to find out. Given is that the fifth chocolate chosen is the first unwrapped chocolate. So first of all, it's a conditional probability, right? Conditional probability. Now, what I'm going to do is, so we don't have to write a lot of stuff, I'm going to say this yellow condition, that second chocolate is the first one wrapped in gold foil. I'm going to call this event A, okay? And fifth chocolate chosen is the first unwrapped chocolate. This case, I'm going to call that B, okay? So these are two things that are happening. The first condition, I'm calling that A. The second condition, I'm calling that B. We have to find the probability of A given B. The formula is probability of A intersection B. That means when A and B both are happening together, right? That's what intersection means. Both events are happening at the same time. And in the denominator, we have the probability of B, the given event. Okay. Now, first of all, let's find the probability of the given event. Okay. What's the probability of the event that is given? Fifth chocolate chosen is the first unwrapped chocolate. What kind of probability is that? Fifth chosen is the first unwrapped chocolate. That's geometric, right? The green one. This is geometric. Okay. With unwrapped being the probability of success, unwrapped being the criteria of success, right? So we are defining success as the chocolate being unwrapped. This is the criteria for success. The first success comes on the fifth attempt, right? So let's find the green probability first. That's event B. What's the probability of that? It's a geometric distribution. Let's write that down first. And for this geometric distribution, the probability of success is unwrapped chocolate. That was 45%. That's 0.45. Let's find this probability. Probability of your first success coming on the fifth attempt. X equals 5. What's the formula for geometric distribution? Q raised to the power R minus 1 times P, right? So if P is 0.45, what about Q? That will be 0.55. So it becomes 0.55 raised to power 4 into 0.45. And that will give you the probability of the first attempt coming in the fifth attempt. You can see what this turns out to be. 0.55 raised to the power 4 into 0.45, and that will be 0.04111778. That's the probability of the given event. That is going to be the denominator. That's going to be the denominator of your formula. Okay. Yes, you can do this using a tree diagram as well, but it's going to be a big tree diagram because you're talking about choosing 5 chocolates. So it'll be like this. First time it's wrapped or unwrapped, right? You can simplify this into 2 outcomes, but for the gold foil later on, you'll have to have 3 outcomes. In fact, gold, unwrapped, or what was the other one? Red. So you have gold, red, unwrapped. That's for the first chocolate. For the next time, you'll have 3 branches with each of them, and then for the next time you have 3 more for each of them. That's 3 raised to power 5. That's too many branches. That will become extremely big. One idea could be that you think of the tree diagram in your head and do the calculations using combinations or factorials. If you are comfortable doing that, that is one possibility. But I think it's easier just thinking of it as geometric distribution for the given event at least. Okay, so that's your denominator. So we have found the probability of the denominator. That's one thing. Okay. Now, out of these, in the numerator, we want the intersection part when both of these conditions are met. Which 2 conditions? That the fifth one is the first unwrapped chocolate, and at the same time, the second chocolate is the first wrapped in gold foil. Now, what would that mean? The numerator, when both conditions are met. Let's think about that now. A intersection B. Now, that will require some thinking now. So what we can say is, we have 5 chocolates. So we have chocolate 1, chocolate 2, chocolate 3, chocolate 4, chocolate 5. Now, the fifth one is the first unwrapped chocolate. The fifth one is the first unwrapped chocolate. So we know for sure the fifth one has to be an unwrapped chocolate, right? That's what we know for sure. Okay. The second one is the first wrapped in gold foil. So we also know for sure that the second one has to be G. Can we say something about the first one as well? If the second chocolate is the first wrapped in gold foil, and the fifth one is the first unwrapped one, then that necessarily means the first is neither gold nor unwrapped. It has to be red, the third possibility, right? Gold, red, and unwrapped. So because we know this is the first time G is coming and this is the first time that U is coming, the first one has to be an R. And now the only problem is in the middle now, these 2 could be anything now, right? For this, we'll have to make cases. What are the possibilities for, what are the possible cases for the third and the fourth chocolate now? Since the fifth one is the first unwrapped one, these 2 can either be red or green. These are the only 2 possibilities, right? So we can say, okay, one possibility is that they're both red. Another possibility is that one is red and the other is green. Another is that the first is green and the other is red, and then the fourth possibility is that both are red and gold. And that's it. These are the only 4 cases that we have for the middle 2 chocolates. The other 3 are fixed, right? These have to be RG, 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 and the last one has to be a U. These are 4 cases that we're getting. We find the probability for each one of these cases, and we add them up together, and that will be A intersection B when both conditions are met at the same time. What are the probabilities going to be now? For red, the probability was 0.25, and for gold it was 0.3. Okay. So the first one is going to be 3 reds. So we can say that is 0.3. How many times? 3 times. So that's power 3. And gold, I'm sorry, red was 0.25. Okay, red was 0.25. 0.25 power 3. Gold was 0.3. That's only 1 here. And unwrapped, that is 1. That is 0.45. That's the first case. Similarly, write down the probabilities for the rest of the cases. In the second one, you've got 2 reds. So that's 0.25 raised to power 2, 0.3 raised to power 2 because we have 2 golds, and then 0.45. And then in the next one, again, you've got 2 reds and 2 gold, 0.25 raised to power 2, 0.3 raised to power 2, and 0.45. And the last one, you've got 1 red, that's 0.25, and 3 gold, that's 0.3 cube, and 0.45. Find each of these probabilities, add them up together. That will give you the case in which you have the intersection, when both conditions are met at the same time. Okay, you can see what these turn out to be. Has anyone done these calculations? Has anyone done these calculations? .25 raised to power 3 into 0.3 into 0.45. That's the first case. .002109. Then you have 0.25 squared and 0.3 squared. Oh, so that's the second case. That's turning out to be 0.002.531, right? 1, 2, 3, that's 0.002. Now the next one is the same, because that's the same powers, 0.002531. And then the next one is 0.25 raised to power 1 into 0.3 raised to power 3. That's very small numbers, 0.0030375. Okay, you add all of them up, and that will give you the result for the intersection part, 0.002531 times 2, that's coming twice, plus 0.002109, and that's giving me 0.010208.5. That's the probability of intersection. And now you can find the final probability, the probability of A and A given B. What would that be? The probability of intersection, that's 0.010208.5 divided by what is given, that's 0.041778, 0.041778, and that will give you the probability. You can see what that turns out to be, 0.0411778, and that turns out to be 0.2479 to three significant figures, that will become 0.248. And that's the final answer that we get.